This lecture, we're going to be talking about the math of graph convolutional networks. We'll give a brief summary of graph convolutions. We talked about it extensively in the previous lecture, but we'll give a little review. We'll then talk about the additional approximations and assumptions that Kiff and Welling made, and then the final neural network layer form that falls out of that. The GCN paper describes the model as a first-order approximation of localized spectral filters on graphs, and we're going to unpack that a little bit using what we learned from the previous lecture. If you recall, our recipe for doing a spectral filter was that we took our signal, which was defined in some original domain, whether it's space or time, or in our case, a signal on nodes in a graph, and we take the Fourier transform of that signal so that it's expressed in this new basis of frequencies. It's just a different representation of the same information. And once we're in this world, we can apply a filter to it by modulating different frequency components. So we can amplify or diminish their intensity, and that applies some kind of filter, which gives us this modified version. And with this modified version, we can take the inverse Fourier transform to go back to our original domain, and now we have this filter that's been applied. In the last lecture, we showed that to take the Fourier transform in the world of graphs, what we need to do is calculate the eigenvalues of our graph Laplacian, and then we can get the Fourier transform of a signal by multiplying by the transform of u, where u stacks up the eigenvectors as columns. And once we've done that, we've essentially put our signal into the space of frequencies. And once we're there, we can apply the filter, which is just going to be some function that amplifies or diminishes various frequencies, and our frequencies are the eigenvalues of the Laplacian. So here we take the Fourier transform, here we modulate it by applying this filter, and then we take the inverse transform by multiplying by u. And this is following the recipe here. And this is what we mean by a spectral convolution on graphs. However, as we mentioned, there are some issues here. Each component is going to depend on the full spectrum, which means a few things. First of all, to calculate u, it's very expensive. To do this eigen decomposition, it's on the order of n cubed, where n is the number of nodes in the graph. Once you have it, u is expensive to use to do these computations because there are n eigenvalues, each of length n, which means multiplication is on the order of n squared. But also, it's inherently non-local because each node influences every other node, and we might instead want our interactions to be localized so that one node can at most influence its neighbors or its neighbor's neighbors, but not every single node in the graph. And this brought us to the work of graph wavelets from Hammond. And what he did was showed that we could just directly approximate this operation of the convolution with some filter using polynomials in our Laplacian. This prevents us from having to do the full eigen decomposition to calculate u and then use u. But it has the other benefit that if we truncate this sum to be only up to the k equals 1 term, that means we get just the Laplacian to first order. And we know that if the Laplacian is to first order, that this is essentially just message passing of nearest neighbors, meaning that a node can only influence at most its nearest neighbors, as opposed to influencing every other node in the graph. This does two things for us. The first is that it avoids us having to do these expensive calculations of the U matrix, either to get it in the first place or to use it, but also it does the localization for us. Now we can revisit the GCN phrase of the first order approximation of localized spectral filters on graphs. Well, first order approximation in this case just means we're taking the k equals 1 as the maximum on our sum. And by localized spectral filters, we understand that now to be as these wavelet filters. And that's sort of stating the same thing twice. By doing k equals 1, we're getting the first order term in L, and that in turn is what is giving us our localization. It's the mechanism of localization. And this is the primary mathematical model of GCN. This is exactly what it's using. It's approximating this convolution operation by these first two terms. We have theta 0, which are some parameters we would need to learn, multiplied by the identity matrix, and then another set of parameters multiplied by our scaled Laplacian. And then this operator, in sum, operates on our original node features x here. And beyond this, there's a few tricks and tweaks that are introduced by Kipf-Welling that solve a variety of problems and result in additional simplifications. And the result of all of this is that we get this nice, convenient layer form that looks sort of like just another neural network layer. And those are what we're going to work through the rest of this lecture. The first tweak here is a result of the Chebyshev polynomials being bounded to this range of -1 to +1. So recall, these are the polynomials we're using in our polynomial expansion. And since they can only range from -1 to +1, we need to rescale things to fit into that range. And Hammond introduces this originally, and he wants to divide by this maximum eigenvalue, here indicated by lambda max. And that gives us this scaled Laplacian, which he used in those equations we just reviewed. And what Kipf and Welling do is they set lambda max equal to 2 and just solve this. And this is the form that comes out. I think there is some analysis done that shows why 2 is a reasonable bound on this eigenvalue. But I think also it could be understood that we're going to be fitting parameters that could adjust for this in any case. But another result is that our i's, the identity matrix here, ends up canceling and we get this simplified form. And then we can just plug this into our polynomial expansion equation with the first two terms. And we essentially get a minus sign, and our Laplacian has now been transformed into the adjacency matrix with these scaling terms of the degree matrix here. The second thing they introduce is that they reduce the number of free parameters that the model has. The original form has theta 0 multiplied by the identity minus theta 1, which multiplies this graph structure piece. But by setting theta 0 equals minus theta 1, we can factor out this common theta parameter, and it absorbs this negative sign here. And what this ends up doing, aside from reducing the number of free parameters, is it gives us this nice factorization where we have our parameters over here, our information related to graph structure and connectivity in this operator here, and then our node features over here. So we factored it into these three separate components of parameters, graph structure, and features. They then introduce a renormalization trick because they note that this new operator that's been formed, that we just created, this I plus the scaled adjacency matrix, that the eigenvalues of this will be between 0 and 2, and therefore repeated applications of this matrix will tend to blow up the scale of the problem. They renormalize this by essentially absorbing the identity matrix into the adjacency matrix. And what this does is it adds a new edge to every node from itself to itself, so a self loop or a self connection. And they call this A tilde. And once they've created this modified version of the adjacency matrix, they can, of course, normalize it by creating this modified version of the degree matrix, which is identical to the previous one, except for now these self-connections are added in, which means that this is identical to the regular degree matrix, except for +1 is added to each of the elements. And then what you end up getting is the I here is absorbed in, and you just get this d tilde inverse root times A tilde times d tilde inverse root. And now we can plug this in. And again, this is just adding a self edge for every node and renormalizing. And plugging this in, we again just absorb this identity matrix in. And that gives us our final form of GCN that you may be familiar with. The output of this layer is this matrix we just created, multiplied by the features, multiplied by the parameters. And then they give this matrix a special name, which is A hat. And this is our simple equation, where this is something like the adjacency matrix, but with the self-connections added in and normalized, multiplied by our features, which is multiplied by our parameters that we learn. And this is our approximation of this convolution operation. And here I just want to emphasize again this nice factorization between the graph structure, the features, and our filters. A very simple and convenient kind of linear form that looks just like a normal neural network layer that's a dense neural network layer. The only difference here is we have this graph term up front, and that by including this graph term, we're doing the message passing operation. Recall that when we multiply a set of features by the adjacency matrix, what we're doing is summing up the features of all of its connections. And in this case, we've normalized the adjacency matrix and included self-connections. So what that means is it includes the features of the node itself along with a normalized version of all of its neighbors. We can also create multi-layer GCNs by stacking the output of one layer as being the input of another layer. In this case, with our first layer, our inputs are X, which are the features, the raw features of our nodes. And of course, on the left side, we have the graph structure represented by A hat and our parameters, W0. And then we, of course, have a nonlinear activation function that's applied to this operation. And then this can become the input to our next layer, where, again, this takes the place of X. So on the left side of that, we have our graph structure, and on the right side of this, we have our set of parameters for this layer, and then our nonlinear activation function, in this case softmax, if we're doing a multi-class classification. One of the things worth pointing out is that in both layers, we're using the same graph structure information to do the message passing, but what's different are the parameters. So in the first layer, it has W0. In the second layer, we have W1. So these are different parameters. They're not shared across the layers, but the graph structure is shared across the layers. The paper wraps up with an ablation study of all these approximations and tricks that it introduces. The point here is to make sure that none of these are going to kill performance for what's originally being done, which is approximating these spectral convolutions. The first thing they do is they look at these approximations, but to higher order, taking k to 2 and 3 and getting values on these benchmark data sets. And you see this kind of sets the baseline. This is what we're going to want to get close to matching. The first trick they introduce is limiting k to 1. And we see that this might hurt performance in some cases, not so much in others. In this one, it seems to help substantially. So it's inconsistent, but it obviously isn't destroying performance. The next trick is the single parameter, where they set theta 0 equals negative theta 1 and factor out to a single free parameter. And we see that this doesn't substantially harm performance. The final trick is this renormalization, where they absorb the identity matrix into the adjacency matrix, or add these self-connections, in other words. And this actually has best-in-class performance on all the benchmarks. And to this, they compare the simple case of having just the neighborhood aggregation information. So this is no self-connections added, just the adjacency matrix. This is a little bit worse. And then here's multi-layer perceptron with no graph structure, meaning no neighborhood information is included, and this is substantially worse in all cases. The takeaway here is that all of these tricks simplify and give us this nice, convenient layer form out the other end, and none of them substantially hurt, and some of them might actually improve things. To summarize, we're calculating graph convolution approximations because doing it the right way is very expensive. It requires the full eigendecomposition of our graph Laplacian, and then once we have it, we have to multiply with this big matrix U, which not only is expensive, but introduces this non-locality factor. GCN uses just the constant in the first order term in the Laplacian to approximate this operation of convolutions. And this has the added benefit that it localizes the signal to a one-hop neighborhood, and this comes from the work of Hammond on graph wavelets. There's a number of other tweaks that are made to handle scaling problems and to get the update equation into this convenient form, and these tweaks are shown to not hurt performance on these benchmark data sets and might actually improve it. With the last two lectures, I hope it's now clear why these are called graph convolutional networks and how exactly they're going about defining this convolution operation and making these approximations so that what was previously impractical becomes practical. This is a really nice way of showing these deep theoretical connections, but then making reasonable approximations and tweaks to come up with something deeply practical.